Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 1 of a unit work, power and energy. So today let's begin with the discussion of the work, and I hope you have did this unit in the class 9 as well. So you might be having a certain idea about the work, energy and power. So let's begin with the work and then we will switch to the energy and power. So the basic thing is what is work, but according to the physics. So according to the physics we can say that work is said to be done by a force when a body undergoes a displacement parallel to the line of action of force. So we must we must go through this two parts. It's the first, it's a displacement, the body should displace. Second, it should displace parallel or anti-parallel to the line of action of force. If this is the case, that means work is being done according to the physics. So in this situation, it is the situation of pandemic COVID-19. You might study it throughout the day while sitting. So it might be very tedious for you, and you may be tired after full day, but you might be surprised to know that this is not work according to the physics. So according to the physics, your work done is zero. I hope you understand this. Yes. But if you are moving out and you are doing something like this is work according to the physics as well as according to the normal day-to-day language. So what I understand is, for the work to be done according to the physics, I have three set of conditions. First, you need to check force is there or not. If answer to this question is no, that means work is zero. Second question, if due to this force a displacement is yes, displacement is there or not. If answer to this question is no, that means work done is zero. And the third question I should ask to myself is whether theta is equals to 90 degree. That means theta should not be equals to 90 degree. This is the third condition. If these three conditions are satisfied, force should be there. Due to force, displacement should be there. And if displacement and force both should be there, their theta could not be a 90 degree. If it is there, your work done will be zero. So from top to bottom you need to assess and you need to check the conditions, that if force is zero, no work done. If force is there but no displacement, again no work done. If force is there, displacement is there, but theta is equals to 90 degree accord, again no work done. I hope those things are clear. So you must be pretty clear about these conditions, first, second and third. Now let's define the work according to the physics. So definition of work is said to be done by a force when a body undergoes displacement parallel to the line of action of force or parallel to one of the components of force applied. So according to this, we understood that work done, that is equals to force into displacement. Basically this is one of the vector, this is another vector, and as you know that work done is a scalar, so it is the dot product. It is the dot product of these two vectors. This work done is equals to F dot S. So let a constant force F is to be applied on the body such that it makes an angle theta with the horizontal, and this body displaced through a distance S. So this is F, and my object has been, let's suppose, displaced from this location to this location. That means my body has been displaced from this to this, and this displacement is S. So if I make a component of this is the theta, then this would be the F cos theta, this would be the F sin theta. So according to the definition, I have understood that this F has been divided into this cos theta and this sin theta, as I know f sine theta is perpendicular to the direction of displacement of the body, and this f cos theta is in the direction of displacement of the body. So according to the definition, this work done is equals to f cos theta into s, or I could say it's a work done is equals to f dot s. I hope this is clear. Even if you are going to calculate work done due to f sine theta, you will find that it's a f sine theta multiplied by s, and in this case you can see this, that theta is equals to 90 degree. So sine 90, what is it? Sine 90, it is 1, but this is not the work done. Yes, so this work done is equals to 0. Sorry, I made a mistake in symbolism. It's a work done is equals to 0 because work done has been defined. Work done has been defined that in this case theta is equals to 90 degree, but displacement x is the 0. Yes, this f sine theta is acting in this direction. This is acting in this direction, and the displacement is in positive x direction. Even you can have this. It's a f sine theta into x into cos theta. This theta is 90 degree, and when it is 90 degree, this work done equals to 0. So various aspect could be there. Various aspect could be there to check the answers, but you must understand that if displacement is there or not. If displacement is in the perpendicular direction, then it is having 0 work done. Yes, great. Let's find out certain important terms and information regarding the work done. As we know, it's a scalar quantity. CGS, unit of work done, it's a dyne into centimeter or the arc. SI, unit of work, it's a Newton into meter, or we can say a joule. And we can have the relation that 1 joule equals to 10 to the power 7 arc, or it's a 1 joule is equals to 10 to the power 7 dyne into centimeter. I hope these things are clear. Yes, this all are the information, this all are the data that you have gone through your school lectures as well as in the 9th class as well. Now let's just find out the dimensional formula of the work done. Dimensional formula of work. This work could be written as F into X. So force, it's a kg into meter per second square multiplied by meter. So this is equals to kg into meter square per second square, and that could be, it's an m1 L2 T minus 2. This is the dimensional formula. This is the dimensional formula of work done. Is it clear? Is it any doubts on this? Anything? No? Great. Now let's calculate the next question. It says the work done in holding 15 kg of suitcase while waiting for a bus for 15 minutes. So it is, the situation is something like this. You are standing over here and you have hold a certain suitcase. Yes, and this is having a weight of 15 kg and all that stuff has been given. But tell me one thing, whether force is there, I should say no. Displacement is there, I should say no. So the work done, it would be a 0. Yes, you were waiting for the bus, so no force is, no displacement is there, and the work done will be a 0. Yes, even if you consider that no sir, force is there, which force, then you might have an answer that sir, mg would be there. Then I understand that yes, mg would be there, but it is acting on this direction. Yes, does it have displacement in any direction? No. So displacement is 0, work done would be 0, and so on. Is it clear? Does it make sense? I hope this is clear. Is it? Great. Now let's look at the next question. It says a circular track of radius r is in a vertical plane, and AB it's the vertical diameter. The work done in moving a mass of m, yes, along the path A to C to B, A, C, B, and G is the acceleration due to gravity. So how will you do this? How will you do this? As I understand that work done is equals to force multiplied by displacement. It is not a distance, it is displacement. So what you need to consider is this is your initial position, it is point A, and this point B, it is your final point. So while you are calculating a displacement, while you are going to calculate a displacement, this is R, this is R, and that's a vertical diameter, it would be a 2R. So the force acting on this object, it's an mg, and the displacement of this object, it's a 2R. So it should be a 2 mgr. That's it, you did it, great job. I hope this is clear. Is it clear? Is it any doubts on this? Is there anything? No? Great. Let's move to the next question. It says that a force of 5I plus 3J Newton is applied over a particle which displaces it from its origin to the point, which is equals to R is equals to 2I minus 1J meter. The work done on the particle is, so force is given, that is F is equals to 5I cap plus 3J cap. A displacement is given, which is equals to 2I cap minus of J cap. I need to find out the work done on the particle. So work done is equals to F dot displacement, that should be is equals to 5I plus 3J into bracket 2I minus J. Yes, I need to perform a dot product of this. While doing the dot product, we understood we just multiply I cap with the I cap, J cap with the J cap. So that should be 5 2s are 10. 3 minus 1, it's a minus of 3, so that should be equals to 10 minus 3, it's a plus 7 of joule. This would be the answer. What was yours? Is it same? Is it same? Are you sure? Great, well done. So let's work for the next question. If force applied F is equals to 3I cap plus 2J cap plus XK cap, and displacement of particle R is equals to 4I cap minus J cap minus 3K cap. Now we understood that force is perpendicular to displacement. This is given in the data. Force is perpendicular to the displacement. They want that find out value of x. So what should I do? Tell me. We have been given force. We have been provided with the displacement. Yes, F is given, R is given. Even one more thing that they have told us, that F is perpendicular to R. We need to find out the value of x. Then we understood that it's an F dot R, which should be is equals to FR cos 90 degree, because they have mentioned it. So let's perform F dot R. Yes, my F, that means force, is 3I plus 2J plus XK, and the displacement R, which should be is equals to 4I minus J minus of 3K. So if I perform a dot product of this two, it would be a 3 4s are 12 plus 2 minus 1, it's a minus of 2 plus x minus of 3, it's a minus of 3x. That should be equals to 0. Why 0? It's a cos 90. Yes, so this is 12 minus 2, it's a 10 minus of 3x, that should be equals to 0. and that should be 3x is equals to 10, and this x should be equals to 10 by 3. I should say it's a Newton. I hope those things are clear. Is it clear? Is it? Is it clear? Are you sure? So can you do this kind of questions? Can you? Is it possible? Are you sure? Are you? Will you be possible? Is it? Great. Next, let's just find it out. The different types of work. We have divided our work or work done in three categories. They are, first is the positive work done. It's a positive work done. Next is the negative work done. And next is the zero work done. So we have this three work done: positive work done, negative work done, and zero work done. So let's look at one by one, starting with the positive work done. So let's look at the positive work. Yes, when I say positive work, we mean that force is parallel to the displacement. So if I understood that if theta is the angle between force and displacement, then my theta should be from 0 to 90. It should be an acute angle. Yes, it is an acute angle. When I say it's an acute angle, yes, its value could be from 0 degree to the less than 90 degree. Yes, it could be an 89. It should not be a 90 degree. I hope this is clear. So positive work signifies that the external force favors the motion of the body. Is it clear up till now? Is it clear? Is it? Great. So which are the cases when I should say that work done is positive? Let's have a look. We can say when a person lifts a body from the ground, the work done by the lifting force. Please do understood this, that let's suppose this is a body and I am going to pull it on the upward direction, then this is the lifting force. This is the lifting force, as you can see in this picture, that a wrestler, that means an athlete is there who is going to lift this weight. So this is the lifting force, and the lifting force in positive direction, the displacement of this box or displacement of this weight is in the upward direction. When both are in the same direction, I should say work done is positive. One more case, when a spring is there and it is going to be stretched, as you can say, as it is being stretched, it is going to be expanded. Yes, this is common for us, that we understood that this is the direction of applied force, or I should say it is the direction of external force. This is the direction of displacement. When direction of applied force and direction of displacement is same, that means theta between these two is 0 degree, and when theta is 0, the work done is positive. Is it clear? Is it? Great. So if the displacement is in the same direction as of the force, then work done is maximum, and which could be written as theta is equals to 0 degree. This work done is equals to F as cos theta, and as it's a cos 0 degree, it would be a 1. It's a work done is equals to F dot S. I hope this is clear. Is it clear? Is it? Any issue on this? Anything? Any doubts? Anything? No? Let's work for the negative work done. It's a negative work done. Means that force is opposite to the displacement. So if theta is the angle between the force and displacement, then theta should be greater than 90 degree, and it should be a less than 180 degree. It should be an obtuse angle. It should be an obtuse angle. So the negative work done signifies that the external force opposes the motion of the body. That the external force opposes the motion of the body. I hope those things are clear. Is it? Now let's look at the examples where I could consider that work done is negative. So when this athlete is lifting the weights, the force of gravity, whatever the weight could be, it would be an mg. Yes, force of gravity is acting in the downward direction, while this weight is moving in the upward direction. I hope this is clear. So as the direction between this force and this displacement is of 180 degree, they are the anti-parallel one. They are the anti-parallel one. So work done by gravity, in this case it's a negative one. So force of gravity, or the work done by the force of gravity, is negative. I hope this is clear. One more case, and very famous one. When a body is made to slide over a rough surface, the work done by frictional force is negative, as you are going to pull this body in this direction. So this is the external force, and let's suppose understood that this box has started moving in this direction. That means it is going to be displaced. It is going to be displaced in this direction. So if it is going to be displaced in this direction, so this is the direction of displacement. This is the direction of force of friction, because we understood from the laws of motion in the sessions and the lectures of friction, we used to have that the direction of friction should be in the opposite direction to the natural tendency of the motion of an object. I hope you remember this. Yes, so as the angle between force and displacement is 180 degree, this work done due to gravity is negative. This work done due to frictional force, is -1. So as we know, this theta is 180 degree. Yes, so work done is equals to Fs cos theta, and when I put cos theta is equals to cos 180 degree, if I replace the value of theta by 180, so cos 180 could be replaced by -1, and this is work done is equals to minus of Fs. Is it clear? Is it? So this work done is equals to minus of Fs. Next, let's work for the very interesting task. It's a zero work done. Now, in which conditions work done would be zero? You need to understand, and you need to remember these three conditions where work done will be a zero. A first condition is that if the force is perpendicular to the displacement. Yes, so if this is the case, this theta would be a 90 degree, and if theta is equals to 90 degree, this is work done which should be F as cos 90. This cos 90 would be a 0, and this is work done is equals to F as cos 90. Cos 90 would be a 0, and this would be the 0. This is 0 joule. I hope this is clear. Is it clear? Okay. Is it possible in practical life that angle between force and displacement is 90 degree? Is it possible? Is it ever happen in the practical life? Let's have a look. Do you remember the case of the circular motion? Yes, in the last, that means in the laws of motion, we have discussed this circular motion. We discussed that one of the force would be there, which is we call as a centripetal force. Yes, which acts towards the center of the circle. Yes, it is the case that centripetal force is acting in this direction. It's an Fc, while if particle is over here, it is going to displace in this direction. Let's suppose write it at x. Angle between these two is 90 degree. So when a body moves in a circle, the work done by the centripetal force is always 0. This is the work done by centripetal force. So there is a misconception by somehow that work done on a circle is 0 because displacement is 0. But displacement is 0, it is the only case when particle has started from somewhere and it has been ended on that point. Even it is not the case. That means if particle has been shifted from this point A to this point, let's name it as a D. So even it has been displaced from A to D, the work done is 0. Why? Because the force and displacement is 0. So don't wait till displacement is 0. It is 0 due to centripetal force as well. Any other case? Any other case where work done could be considered as a zero because force and displacement is at 90 degree to each other. Any other case? Have you remember the projectile motion? It was y-axis, it was x-axis. We used to throw an object something like this while making an angle theta and something like this. Is it? Sorry, this is an angle theta with certain speed u. So which force does act? Which force does act on the projectile while doing projectile motion? Yes, some of you might remember this, that this is the displacement from here to here. This is the displacement. We used to have this distance as a range, and only one force was acting, that is of mg. Throughout the journey only one of the force was acting. So if you look at this, this is the displacement, this is the force acting. This both are perpendicular to each other, and when these two are perpendicular to each other, the angle between these two is 90 degree, and when angle between these two is 90 degree, this work done would be equals to 0. I hope this is clear. Is it clear? Is it? Are you sure? Great. So this is the second case where work done would be 0. We can have many more cases, even in the case of tension, when certain stone has been connected, something like this. That let's suppose a certain stone is there, it has been connected by string, and we made a pendulum kind of thing. And in this case, when let's suppose it is reaching over here, yes, even in this case tension is acting on this, particle is displacing in this is the displacement at this instant. So this is 90 degree, and this work done is 0. Even if you take any position, let's suppose the particle is over here, that means Bob is over here. This was the direction of tension, and this was the direction of displacement. Angle between these two is 90 degree. So work done would be a 0 degree. I hope this is clear. So there are many cases where force and displacement is 0, and as force and displacement is 0, work done is 0. Yes, this is very interesting case. Now let's look another situation where work done is 0. Let's suppose if there is no displacement, that means you are applying a force. A force is there, but there has not been displacement. So let's understand the case when a person tries to displace a wall by applying a force, and if it is not moving, then the work done by the person is 0. Even you can try doing it at your home. Let's suppose wherever you are sitting, just find out one wall and push it. Is it going to move? No. If it is not going to move, that means force is there. You say, yes sir, we have applied a ample amount of force. Does it have any displacement? Your answer should be no. So that work done would be a 0. So always remember those three conditions. First, check from top to the bottom. Now let's understand the third situation when 0 work done would be there. If there is no force acting on the body, if F is equals to 0. If F is equals to 0, that means no force is acting, and if no force is acting, it is just the violation of our first condition. So that work done would be 0. So it is the case when the body is moving with uniform velocity on a horizontal frictionless surface. So it is something like this, that this body is there and it is moving with a speed of, let's say, 20 meters per second on the straight path. So according to the Newton's first law, force acting on it is 0. Yes, you must understand that this is mu equals to 0 surface. It's a frictionless surface. And if force is 0, work done due to this force is 0. Yes, I hope these things are clear. Is it clear? Is it? Any doubts on this? Anything? Is there anything? No? I hope those things are clear. Can I consider that this all are clear? Yes? Great. Now let's work for the applications of work. In this session, in this topic, we are going to look at the certain very good applications that have been asked directly or indirectly in the numerical. So we are just going to summarize this at a first, and then we will switch to the numericals. So please do one thing, have your pen, have your paper, and start doing it with me. Yes, because this will help us to build a concept as well as to do the numericals. So let's look at this. The work done by a force in various situations. So let's suppose understood that this is mass m, a block m, and it has been lifted from ground to a height h, by using a minimum force F. So what you need to do is you need to find out the minimum work done by the lifting force. So what you are supposed to do is you are going to pull it on the upward direction. So it's a force into displacement. Why I have written a theta over 0? Because this has been force is acting on this direction. Displacement of the force that we call as an h, even it is in this direction, and the theta between this two is 0 degree. So when and where force is applied, displacement is in the same direction. If these two are in the same direction, this is equals to f dot s, and this f could be represented as an mg, s could be represented as an h, and that's why work done due to this force F, it's an mgh. Is it clear? Now one more thing I need to focus is that if I consider work done due to gravity, so force of gravity would be acting in downward direction, but my particle, that means my box, has been displaced in this direction. In this situation, theta would be equals to 180 degree, and when it is 180 degree, it's a work done is equals to F gravity into H into cos of 180 degree. Cos 180 would be a -1, so that should be is equals to minus of Fg into H. This is equals to minus of mgh. I hope these things are clear. So work done due to gravity, in this situation will be minus of mgh. Got it? Yes? Well done. Let's look at the next application. It says that a bucket full of water of total mass m is being lifted up with uniform velocity using a rope of mass m. Please have a focus that a bucket is having mass m, capital M, of water, and it has been pulled up, it has been lifted up with a uniform rope of mass small m and length L. So what you need to do is you need to find out the work done. So what I understood is that this is the rope, and this rope is having mass m and length L, and it has been a bucket is there, and this bucket is having mass m. So what you need to do is you have been lifted up for the length L. So what I could understood is work done, that is the force acting on this, it's an mgh, that means m into g multiplied by for length, it's an mgl. But when you understood and when you take a case of mass m, you must understand that this mass m having distributed over this position, this is what we call as the center of mass concept. It is the point where we assumed to be that at that point total mass of the body is going to be concentrated. So this is the length L by 2, it's a center point. So work done to carry this, it's a work done 1, it's a work done 2, work done to carry this, it's an mg into L by 2. So the net work done will be equals to mgl. It's a bucket, and or that means to carry the water of total mass m, and the second one is for the rope of mass m into g into L by 2. I hope this is clear. Is it clear? Okay, so let's do this. This is a rope having mass of 10 kg, length of 10 meter, and this is a box. Let's write this m1, so I can write this as an m2. This is of 50 kg. So I have been asked that find out to lift the system of rope and block by distance of 10 meter. So what I understand is that on this rope the mass has been distributed thoroughly. So what I need to consider is I need to take a point, and that should be L by 2, which in my case it would be a 5 meter. So the total work done would be equals to m2 multiplied by g multiplied by length plus it's an m1 multiplied by g multiplied by L by 2. So this is equals to m2, which is 50 into 10 into 10 plus m1, it's a 10 multiplied by 10 multiplied by 10 by 2, it's a 5. So this is 1 2 3, it's a 5000 plus 10 10 100 plus 5, it's a 500. So this is equals to 5500 joule. I hope this is clear. Is it clear? Is it any confusion in this? Anything? No? Ready for the next? Great. Let's have a look. A very interesting, and sometimes this can create a very good amount of confusion in students' mind. So please look at this very carefully. It says that a pendulum is there, and a pendulum of length L carries a bob of mass m. This bob is pulled aside through an angle theta with the vertical by a horizontal force. That means we are talking about this force only. So what you need to do is you need to find out the work done. But as you can see that here there are two forces. One of the force is the mg, and one of the force is work done by this force F. So let's understood first the situation. What you need to understood is that this is the length L of the string, and this bob has been shifted from this position A to this position B. Now as it has been shifted, if I find out the displacement, it is just the displacement that I have denoted by h. So if it is h, the remaining term of the string should be called as the L minus h. This is the L minus h. If you can see this right angle triangle, shall I give them a name? Let's suppose this is A. Could not call it A. It's an E. This is E, and this is F. So if I take this triangle, what would be the cos theta? What would be the cos theta? The cos theta should be is equals to L minus h divided by L. I hope this is clear. So this L minus h should be equals to L cos theta, or I should say h is equals to L minus L cos theta. This is h. So if this h is equals to L minus L cos theta, so this part could be written as L cos theta. Even we can do this with the help of resolution of vectors. So if this part is L cos theta, this part is L sin theta from this to this. So now what I need to do is First, I need to find out the work done due to gravitational force. It is work done is equals to, we have a term, it's an m into g into h. So now height h can be written as L minus L cos theta, and that could be represented as m into g into L minus L cos theta. If I consider that mg is acting in the downward direction, and it is always acting in the downward direction, so that could be represented by minus, because work done is negative, and this should be mgl into bracket 1 minus cos theta. This is the work done. This is the work done due to gravity. I hope this is clear. This is the work done due to gravity. Yes. Now, what about the work done due to force F? What would be the work done due to force F? So, if you understand this, look at the diagram carefully and you will find your answer. What is the direction of force? I should say positive x. What is the direction of displacement? I should say positive x. So if theta is 0, it would be a much easier work done due to force F. That should be is equals to F multiplied by L multiplied by sine theta. That's it. You did it. Great job. I hope this is clear. Yes. So work done due to external force, or according to the data, it's an horizontal force F. It would be a F into L into sine theta. That's it. Yes. So work done by the gravitational force that we have already derived, it's a minus of mgl into bracket 1 minus cos theta, and the work done by the horizontal force F, it's a F into L into sine theta. Is it clear? Is it? Are you sure? Great. Let's have a question on this. Have your pen and paper ready and do it with me. So the question is that, let's suppose a pendulum is there, a length of the string is 1 meter, and it has been gone through this, and from here it is making an angle of 60 degree. So what you need to do is find out. Now it has been displaced. It has been displaced because of certain horizontal force, and that horizontal force would be of 5 Newton. So what you need to do is you need to find out work done due to gravity. Find out work done due to gravity in the given situation. So while I consider the gravity only, or I am interested in the work done due to gravity only, so what I understand is, now I understand that work done due to gravity, it is equals to, so this is the initial position, this is the final position, so this is the displacement. Why I considered this? Because I understood that mg would be acting in this direction, so my work done could be either parallel or anti-parallel to the force. So mg is downward, h is upward, so that should be, first it would be a minus, it's a minus of mg into bracket L into bracket 1 minus cos theta. So this is equals to minus of m into g into length is given, it's a 1 meter, into bracket 1 minus cos 60. Cos 60 is half, so that should be is equals to minus of mgl into bracket 1 minus half, it's half. So this is minus of mgl by 2. This is the work done due to gravity. I hope this is clear. Is it clear? Is it? Okay. So now let me add something. Find out the work done due to F external force, that is of 5 Newton. So this F is acting in this direction, it is acting in horizontal direction. We understood that this is L, so this would be L cos theta, and this would be the L sin theta. If it is there, what I need to do is work done due to force F, it's an F into L into sine of theta. This is work done due to force F. So this F work done due to force F is equals to F into L sine theta. Force is the 5 Newton. Length is the 1 meter. Sine 60 should be a root 3 by 2. It's a 5 root 3 by 2 joule. This is the work done due to force F, and this is the work done due to force of gravity. I hope this is clear. Is it clear? Is it great? Do you understand this completely? Any doubts on this? Any doubts up till now? Is there anything? Is there any doubts on this? Anything? Are you sure? Are you sure? Great. So let's look at the next application. Yes. It says that a uniform chain of mass M and length L is suspended vertically. This is the situation. This chain is having mass M and this is the length L. Yes. The lower end of the chain is lifted up to the point of suspension. So what you are supposed to do is you are going to hold this, and just you are going to do something like that, that you are going to pin up, or you are going to screw this end over here. So the situation would be something like this. So for this you need to find out the work done by the gravitational force. So the situation is work done by the gravitational force, work done by the gravity is, this is work done, that should be is equals to minus of mgh. This is my master formula that you must understand. Now in this kind of situations that we have already discussed in the previous slides, that center of mass would play a role, and center of mass, it is the point where complete mass of the particle, that means of my system, has been assumed to be concentrated, and when it is assumed to be concentrated, it is at the midpoint. So initial work done, or initial, it is mg into L by 2, but in negative direction. This is initial. Initially the situation would be something like this. It's an mg L by 2. Now this two parts, the one part is of L by 2, the another part is of L by 2. So the final situation is it's a minus of mg into L by 4. Yes, it looked like this. So what you need to do is you need to find out that h is the height gained by the center of gravity of the lower half of the chain with respect to initial position. So the difference is initially center of gravity was at there, it's an L by 2. Now it is at L by 4. So work done is you need to shift it from L by 2 to L by 4, which is L by 4. So work done by the gravitational force in this situation is minus of mg into L by 4. This is very, very interesting. Yes, when we have gone through the numericals, you will find the value of this. That's the work done due to gravity would be equals to minus of mg L by 4. I hope this is clear. Is it clear? Is it great? Now let's look at the next application. It says that a uniform chain of mass m and length L rests on a table having 1 by nth part of its length hanging down from the edge of the table. You need to find out the work done by the pulling force to bring the hanging part of the chain on the table. So how should you do this? First, understood that the situation is this is the part which is resting on the table, and this is the part which is 1 by nth part of the length, total 1 by nth part of the length, which is hanging. So, and you want to pull this from here. so that even this part would be on the table. So what you understand is that only this part is hanging. That means you need to write down it's a minus of m into g into h. You need to do the work on only this path. That must be understood by you guys. That because this is only the same position. This were on the same position initially as well as afterwards. But you need to do a work on this part. It's a hanging part. So what you need to do is find out the mass of this part which is hanging. So what you understand is that total mass, m is the total mass. Yes, and only the 1 by nth part is hanging. So mass of that part, mass of the hanging part, it should be an m divided by n, as they have used a small m, it's a m by n. Yes, this is the mass of hanging part. It's a m by n. I hope this is clear. And where is the center of mass point? Where is the point of center of mass? It's as it is the 1 by nth part, 1 by nth part, and the center of gravity would be at the half of the point. It should be an L by 2n. So if I club this everything, let's have a look what would be the situation. So work done that I understood, it was the minus of m into g into h. So I have replaced my mass by the m by n. It's a g, it would be there, and h, it would be a L by 2n. Yes, so this work done would be equals to mgl by 2n square. This is a very pretty application. You are going to have many numericals based on this. I hope this is clear. Is it clear? So are you guys ready for the one of the applications, one of the numericals? Let's have a look. That this is the chain. And you can see this, that this is the L by 2 of the chain, and this the remaining L by 2. The remaining L by 2 is resting on the table. You need to do that, find out work done required. Find out work done required to bring this hanging part, this hanging part of the chain on the table. So one of the approach of this question is based on the formula. But first I will like to go with the concept. Yes, so let's assume that mass of the chain, or I should say mass of the complete chain, is capital M. I need to work on this only. And this is only the half of the mass. So I must understand that this is my master formula. Work done is equals to mgh. This is the master formula on which I am going to do this. So my interested mass on which I need to perform a work, it is only half of the mass. That means it should be an m by 2. So I have done for the m. Now let's suppose I am working for the h. So h is the point of center of mass of hanging part. Yes, in certain slides you have seen it's a center of gravity, in certain slides it's a center of mass. Both are the same thing. When we are talking about, or when we are discussing about the smaller objects, so you can use any of this. Yes, so don't worry for that. Yes, now the h would be center of mass or center of gravity would be at the midpoint, and this is the distance. The distance is L by 4. So this h is equals to L by 4. Now let's just put up the value. It's a m g h, that should be is equals to m by 2 multiplied by g multiplied by h, and this h would be equals to L by 4. It's an mgl divided by 8. I hope this is clear. This is clear. Now this was one of the approach. Approach number 2. It is just the formula based approach. Yes. So for the formula based approach, what you are supposed to do is that work done it's equals to mgl by 2n square. While you using this formula, you must understand n, it is the part of the total length, which is hanging from the table. Yes. So it's an mgl by 2n square and when I say it's an mgl by 2n square, this is m to g multiplied by L divided by 2 into n. It's a 1 by 2. That means n would be equals to 2. Yes, it's a 2 square. So this is equals to mgl divided by 2 into 4. That should be is equals to mgl by 8. This was the answer. So if you remember this, yes, you can do this. If you have forgot this, you can go with the concept. Yes, concept would be always there. But if you forgot it, if you forget the numerical, or if you forget the formula, you can go with the concept. And if you have remember the formula, yes, just go with this. It will save our time, and that time that has been saved can be used to do certain other questions which are critical or which take a bit longer to calculate it. Now let's look at one more question based on the same principle. It says a uniform chain of length L and mass m is lying on a smooth table and 1/3 of its length is hanging vertically down over the edge of the table. Okay, so this is the situation. This is the chain and this part is hanging. This is the 1/3 of the total length. Yes. So if g is the acceleration due to gravity, the work required to pull the hanging part on the table. Yes. So what I need to do is it's an work done is equals to mgl by 2 into n square. You understand that n equals to 3 in this case. So if it's a 3, it's an mgl by 2 into 9. That should be is equals to mgl by 18. This is the work done required. I hope this is clear. Is it clear? Is it clear? Great. So let's just wind it up this session over here. We were discussing all the work done due to fixed forces. These are not the forces which are keep changing. In the next session we are going to discuss the work done by variable forces, but before you tune into that, please make sure and ensure that you have gone through this session. Yes, we are doing very critical parts of the physics. Yes, the 3 of the segments. One is the laws of motion that have been completed. Second, that has been started, it's a work, power and energy. And the next unit, it's a center of mass and rotational motion. This will be the 3 unit. This is a club which creates a lot many concepts of physics. Probably we can say this 3 units covers approximately 35 to 40% concepts of physics, and based on this concepts the overall another physics is running. So please have a hold on this, have a grip on this. You must need to attempt so many questions that can make our task, our journey of physics would be easier. Thank you. Have a good day. Take care.